Okay, following Clementine and Daniel is a pretty tough act to follow. It does have some advantages though. Clementine and Daniel spoke a lot about mitigations from Rowhammer, and I have blogged extensively on the subject, so if you're interested in why the mitigations don't really work, come see me after the talk. Anyways, I'll be talking about how you can use microarchitectural design to break kernel mode address space layout randomization and a bit more. And I'll try to be painting a bigger picture of what is happening here. So this talk is about microarchitecture attacks on KASLR. If you don't know what microarchitecture is, it is the implementation of architecture, which leads to the natural question, what is architecture? Well, architecture in this sense is what CPU developers promises to software developers. And microarchitecture is how that is implemented. There are some leeway in how you can implement the microarchitecture, whereas the architecture is promised and described. KASLR, kernel mode address space randomized layout, randomizes addresses in the kernel to prevent exploits on the kernel. We'll go into a bit more about how that works in a moment. And when I use the word design in the title of this talk, I actually mean it. It's not just to sell the talk. The thing about this microarchitecture is that a lot of energy goes into designing the microarchitecture of a CPU, and the features that we end up using to break these things were actually decisions that are made by design. They are meant to be there. They have some, unfortunately, side effects that we can use. So in this particular talk, I hope to paint a bigger picture. This means that I will not go as much into details as I might like. It's more of an overview thing, sort of like the last talk. There is one thing that I'll caveat out here. I will not talk about software attacks on kernel mode address space randomized layout. So I will mention it once though, but I won't talk about it in general. Short, who am I? My name is Anders Fogh. I'm a principal security researcher for DData Advanced Analytics. I used to be an economist with a hobby, and nowadays you can reach me on Twitter or by email. The Grok thinks that I learned assembly language because it was the only functional language in Denmark. There is a matter of truth to it. So if you hear me speak with a 16-bit twang, it's because I'm old. So paging in modern operating system functions pretty much this way. Each process has its own virtual address space. And in this address space, there are the modules that they're using. In this picture, we have Calc and Office. And if you have a shared library that both processes use, they're in there as well. And in all processes, you'll find a mapping of the kernel. The kernel is protected here, and there is this line between them. I'll talk a bit about how that line comes into play in a moment. They use the paging to map it to physical memory, and here is just a black box. We'll go into that in a moment. And you can see that the shared library, as well as the kernel, is only mapped into physical memory once. So the summary here is each process has its own virtual address space. Paging translates virtual addresses to physical addresses. Shared libraries map to the same physical address. And the kernel in current operating systems is mapped in each process. So now how the black box works. We start at the top. Talk a bit about the virtual address. It's listed here as 48 bits, and most of your software developers out there will know that modern systems uses 64-bit pointers. The secret to this difference here is that the upper 16-bit is actually only decorations. They take the same value as the 47th bit, meaning that you will never have an address with a bit that is not 0 or 1 in the upper 16-bit. Just decoration. This is why we have virtual address space of 48 bits. So paging starts with the CR3, that's a control register in the Intel line CPUs. And each process has its own value for this register. And this register chooses a table to which to start the translation from physical to virtual addresses. In this table goes the upper 9-bit of the virtual address. As you can see, it's marked green. What comes out from this table lookup is the table for the next lookup. The entry in the next table is the blue, and this goes on until we reaches the last table, the page table, where we actually get the physical address. Maybe you saw it in Daniel and Clementine's slides as well. Here you get the physical address. The lower 12 bits, however, are identical between the physical and virtual addresses, and this is what makes up a page. A page is typically 4,096 kilobytes. Interesting thing here is there are other page sizes that just bought the page table translation earlier, then more than 12 bits are in the pages. I will not talk about that, but it does exist. I will just, in this talk, assume that all pages are 4 kilobytes. So the last entry in the page table does not only include the physical address. This is the gray part of the figure here. It, as Daniel and Clementine noted, all has some ignored parts. That is the red parts here. It has some parts for management. I will not be talking about those today. It also has some parts that determines how the memory is cached. I will not be talking about that either. What I will be talking about is access rights. That is the green parts. There are 3 bits related to access rights in the page table, in a page table entries. And they are the NX bit, which disables execution for memory. It's the supervisor user mode bit. When the bit is set to 1, only a supervisor has access. That is, kernel mode has access. If the bit isn't set, the user has access as well. And then there is the read-write bit. If the bit is set, you can also write the content of this page. Otherwise, you can read it only. So security through this paging systems functions in the following way. If an access is made by code running with user privileges to an address marked in the PTE, as we saw before, a supervisor, then a page fault will be thrown. The kernel gets a chance to defend itself or handle the page fault however it likes. The kernel in each process is protected from read-write access in the same way on modern operating system. It's just the supervisor bit in the PTE that protects the kernel from user mode access, despite of it being mapped in the process. This kind of system has a problem. And the problem is that the page tables themselves are stored in physical memory. Access to memory is really, really slow compared to what modern processors is capable of chewing through. And to this problem, there's a microarchitecture solution. And the microarchitecture solution is we cache the page table entries. And they are cached for each core in exactly the opposite direction that the page table lookup goes. Probably the idea behind this is that if we can find a page table entry in the caches, we'll save more than if we find, say, an entry for a higher level table. Also, it, of course, has the no, never mind. If it's not found in any of these 4 level of caches, the lookup will actually be made in physical memory. This is what you need to, the situation you need to get for a row hammer exploit, as you saw in the last talk. And then it will be slow. So let's move on to what and how does KASLR, kernel mode address space randomization, work. Well, I'll do it by example. Say you know the address of a relevant, security relevant address in the kernel, say the B test signing enabled variable in the kernel. The example here is not accidental and not something I'm pulling out of my hat. In fact, this variable used to exist in that fashion in the Windows kernel, and an APT group used an exploit to set this variable so they could load their own driver without having a certificate for it. So it's not something I'm pulling out of my hat. You would know the address if you just disassemble the kernel, at least. So if you have a bug that allows you to read-write anything anywhere, you'll be able to change this variable like the APT group did and load your own driver into the kernel despite of not having a valid certificate for it. Historically, the address of the kernel itself was hard-coded, and with a hard-coded kernel address, the relatively address that you can get with your disassembly, you can figure out where this byte is stored with your read-write anything anywhere bug. You can change the variable and load your driver. It's fairly obvious. That is I tried to illustrate it in the figure on the right. Here the kernel is loaded in the kernel mode part of the address space, and the red dot is the address which you will use to enable test signing if you're an attacker. So the idea behind kernel address space layout randomization is, well, when we boot the system, we load the kernel at a different virtual address every time using the page tables to do that. So this means that the address you got from the disassembly, the relative address you get from the disassembly, won't help you anymore. If an attacker guesses the wrong address of the kernel, he will trigger a page fault accessing memory that is not mapped, and usually this system either blue screens or sec faults, depending on what kind of system it is, turning the attack into a denial of service instead of the system getting owned. That is the core idea behind kernel address space layout randomization. So to summarize the background, the kernel is mapped in each process. User mode cannot access the kernel because it's marked as protected by page tables. The KASLR randomizes the page table where the page tables are located. That should read the kernel are located so that an exploit cannot know where it should patch something. That means that even in the presence of a bug, the kernel is safe. Except I'm painting a picture here. This is my favorite painter, Bob Ross. He likes to paint pictures as well. And he famously said, there are no such thing as mistakes, so this is not a mistake, this is a happy little accident. And the happy little accident was Hund, Willems, and Holz in 2013 from this university here. And they figured out, well, we have these caches. What happens if a page is cached? And we all know why caches are there. They're there to make it faster, so we would think that if a page is cached, accessing it will be faster. And so it is. If we measure how long it takes to access a page, depending on at which level the entries in the page tables are cached, we'll get different timings. The large blue column on the right side of the screen is the uncached time. So you can see that is significantly higher than the other times, other access times. So how do you measure the time of a page fault, the time that it takes for the system to traverse the page tables and find out there's no access rights to access this process? Well, you do it with code that looks something like this. You start a time, you get the current time in clock cycles, then you access the kernel address, a page fault is thrown, and you grab the page fault in an exception handler and read the timestamp again, and then you know how long it took to read this kernel memory. So how does the double page fault attack basically work? Well, you time accessing a kernel mode address from user mode. It has to do the page table translations. This has two effects. The first is it loads the paging caches, and the second is it triggers a page fault that is thrown down to user mode so you can measure the time, as we just saw in the code. This generates a baseline for how long it takes to do an uncached access to the kernel memory. So now we do it again. And remember, we just loaded the paging caches. So we should think that the second time we access the address, it'll be faster than the first time. Except non-mapped pages does not get cached, meaning that we have a timing difference here. If the second time is faster than the first address, well, then probably this address is mapped. And then the attack goes on. It just repeats step 1 through 3 for all possible kernel addresses. And from the pattern of mapped and unmapped pages, we can actually tell where the kernel is. So, execution time on modern multi-core CPUs are not deterministic. There is a slight variation depending on which order the instruction comes in, how the DRAM is working or not. So there is a tiny bit of noise in execution times on modern CPUs. This particular attack raises a page fault and forwards it to user mode. And this has a lot of overhead in it. There's a lot of code to be executed, and there's a lot of stuff going on with interrupts and things like that. Meaning that there's a lot of space where these tiny random noise can add up, meaning that the result that we get is very noisy. The solution to this problem is we just repeat the attack again and again and rely on this law of large numbers and statistics that says if we have enough observation, we will be able to figure out the real mean given that we have independent observations, which we'll have in this case. So the attacks work kind of well. It works in a couple of minutes, and we can de-randomize the kernel and we can run our attack again if we have the bug for it. It is, however, relatively easy to fix. When a page fault is thrown, a callback is made into the kernel, and the kernel gets a chance to handle a page fault. And among the information that the kernel gets to process a page fault is the address where the page fault happened. And if this address turns out to be a kernel address, and the client who caused the page fault is a user mode application, then we're probably looking at double page fault attack, because it tends to be that user mode application does not try to access the kernel because that just causes faults. So if it happens a lot, we can start buggering around with the client that is doing this, like terminate the process or add noise, whatever we like to do. And if it isn't, we just handle the page fault the way we actually usually do it. So we can easily fix the double page fault. So with this fix, we're safe even if there's a bug, and even if the double page fault, even if the attacker knows the double page fault attack. Well, gets kind of interesting here because there was a happy little accident. And this is TSX. Yang, Lee, and Kim in 2016 presented an attack on KASLR that used TSX. TSX was added with Haswell microarchitecture, so it's relatively new. TSX stands for Transitional Synchronization Extensions. The purpose here is synchronization. Imagine two threads accessing the same variable, one of them is writing, and if this happens simultaneously, say on multiple cores, then inconsistencies can arise. The classic solution for inconsistency of this nature is synchronization, say mutex, semaphore events, stuff like that. This is usually very slow because the scheduler gets involved and stuff like that. And another way that has been classically solved is locks. You lock the entire memory bus, and that is usually a bit faster than mutexes and semaphores, but it's still pretty slow. Imagine 24 cores working on a database, and all of a sudden they can't do any memory accesses until the synchronized access is done. And this is what TSX tries to solve. They simply try to do the memory access and detect if there's any simultaneous operation. If there's any simultaneous action, they will abort it and reset it and let you retry it. And the thing is, true simultaneous access is rather rare, and this ends up meaning that only rarely will TSX really abort a synchronous access, and this turns out to be much, much faster than, say, locking the bus. So how can we time an abort in TSX? Well, here we now have this wonderful if statement instead of the try except, and otherwise everything looks exactly the same. Why is TSX cool for breaking KASLR? Well, if access is illegal, that is user mode trying to access the kernel mode, TSX will abort without generating a page fault, meaning that the page fault is gone. The first cool thing about this is that we'll get less noise because we have less overhead, the attack is much faster, and the mitigation that I just presented you for the double page fault will not work because the page fault handler does not get called. And it actually works because even though we're in this TSX section, paging cachers are still loaded on access. It has another advantage here is if we access kernel mode memory with a jump instruction, it gives different results on other memory access, meaning that we're able to tell if memory is marked as executable or not, meaning that we can find out if a given page in the kernel is marked as executable or not. So this gives us more information than a double page fault attack. There are some problems with the TSX attack. The first is that it might be possible to detect the TSX attack heuristically using performance counters. When an instruction causes an abort, the number of events are generated related to TSX, and and in all other cases a TLB lookup miss event is generated, we can measure those with the performance counters, and we have a possibility to heuristically detect TSX. But probably the most important disadvantage of TSX attack is that it's not very common. There are a few i5s, a few i7s, and a few Xeon computers that actually supports TSX, meaning that the real supported base of TSX is relatively small. Meaning that, in end effect, we are something like almost safe. Except there was a happy little accident. So, Bruce, Maurice, the two previous speakers, myself, and two others, figured out that there was a prefetch instruction in the instruction set of Intel computers. There are 5 of them, and they serve the purpose of speeding things up. And how do they do that? Well, the prefetch tells the memory management system of the CPU that the software would like to use this memory soon. So why will this work in the first place? Well, modern CPUs are multiscalar, a superscalar. They can proceed with other instructions while loading the memory, meaning that we can tell in a moment we'll need this memory, please cache it, and then we can do other instructions until we actually use the memory. So we have a speed up here. That is the purpose of the prefetch instruction. Why is the prefetch instruction cool to break KASLR? Well, prefetch instructions are hints, meaning they don't cause faults or aborts. They terminate completely silently instead. However, the prefetch instructions also need to traverse the page tables, and they load the paging caches just as well. Meaning that we can use the double page fault attack with the prefetch instruction instead. And unlike the TSX, the prefetch instructions are very, very old indeed. They were introduced with 3D Now by AMD sometimes early 2000s, I think, and they are in all current CPUs. There's another advantage to the prefetch instruction here is prefetch instruction does not match well with performance counters. There used to be performance counters for the prefetch instruction. They're gone. It seems like Intel are happy that we can all optimize our software with the prefetch instructions without performance counters help. So it maps very poorly to performance counters, meaning that the attack is far more stealth than the TSX attack. So how do we time a prefetch instruction? Well, you can see the code is almost perfectly reduced. There's no if statement, there's no branching. It's just start the timer, get the current time, call the prefetch instruct, get the end time, and you got the result you need for the double prefetch attack, for the double page fault attack, just using the prefetch instruction instead of a page fault. There is a problem with prefetch instructions. That is, prefetch instructions are data only, meaning that we have no way to tell if memory is mapped in the kernel as executable, meaning that we get a bit less information than we would get with the TSX attack. So, is all lost? Well, maybe not. Intel built into current CPUs a feature called SMEP, or supervisor mode execution protection. And the idea here is it prevents execution of memory allocated by a user with user mode privileges from being executed with a thread having kernel privileges. The idea here is it forces an exploiter writer to find a way to move her code into the kernel mode before she can call it, meaning that something like patching an indirect, the address for an indirect call won't help here. The exploit writer would have to move his code into kernel mode before he can do that. And there's SMEP. SMEP is supervisor mode access prevention. That is the exact identical thing for data. and it prevents the kernel from using user-allocated data. And this essentially prevents an exploit writer from using database attacks, such as return object-oriented programming. And you need to get her data into the kernel before she can launch an attack using data. So this is kind of getting old, isn't it? There was another happy little accident. So most operating systems have so-called kernel direct mapping. The major exceptions under the modern operating systems is Windows. We'll get back to Windows in a moment when I'm done with Linux. The thing here is these operating systems map the entire physical memory into the kernel part of the address space. It does so that the kernel have access to any memory at any time for any reason. And this is just plain convenient. Among the things that it need access to are the page tables to allocate and deallocate memory, stuff like that. So you have the entire physical memory inside the kernel space. So now we have the attacker already has her data or code in the kernel mode. It's just a matter of where is it. And the prefetch instruction is quite helpful in that connection. The prefetch instruction allows us to use a kernel mode address to load the data of that address into the cache. It does not check that it's called unprivileged, it just does it. So what we need to know here is that accessing memory that is already cached is faster than otherwise. So now we can iterate through the kernel direct physical map, prefetch one address after another, and then test if an address that we're interested in having in kernel mode is now fast to access, and if it is, then we know where it's mapped in the kernel, and we have a perfect SMAP and SMEP bypass. So now that we have seen what is academically possible, let's turn to a real-world KASLR break using these methods. It goes back to NISM in 2016, and NISM had a real-world write anything anywhere bug. The mechanics of the bug relied on a combination of using the Windows 32K module, any of the next window functions, in a combination with NT set window long pointer. I'll not go into how the exploit actually works. It just suffices to know that it's a write anything anywhere type of bug. Using this information, NISM had a very interesting way of gaining kernel privileges that is not quite unlike what Daniel and Clementine presented in the last talk for Rowhammer. They patch the page tables. And before we find out how this works, we need to talk about a bit how Windows uses the page tables to modify the page tables. So each process always maps its own page tables at a given address, or well, it used to. And this allowed NISM to know exactly where the page tables are, and knowing where the page table are, having a write anything anywhere bug, well, you can find the supervisor bit in the page tables themselves, flip that bit, and you have root because you can access any memory anywhere in the system. You can read, write, execute anything you like. So you have root, pretty much the same way the original Rowhammer attack worked, this time with classical software bugs. So Microsoft had a solution for that. They added KASLR to the self-reference. They randomized using the upper 9 bits of the virtual address, meaning that now NISM would have to guess a value in 1 in 265, 56, and if you guessed wrong, he'd just blue screen the system. NISM is a smart guy, and he responded by using TSX and the prefetch attacks to find the address of the self-reference in the kernel space, and turns out both works. The prefetch is faster, probably because the code is much cleaner, there's no aborts and stuff like that. So it's not like that we're totally defenseless yet. The thing is, the 3 attacks that I presented so far all work because of 2 things. The one is the paging caches, and the second is that the kernel is mapped into every process and only protected by the supervisor bit. So paging caches we cannot do very much about, at least not without a very steep performance penalty, but we don't actually have to have the kernel mapped in every process. So what happens if we map the kernel in any other process? This method was suggested by Yang, Lee, Kim, Gross, Maurice, myself, and others. And it works something like this. In each process, you now have, I call it a microkernel, that's the wrong term, I don't know what the right term is. You have a very small kernel that has a stub for function that must go on in the current process, and then it transfers to the kernel process, the real kernel process. And the real kernel process is in a process of its own, and thus we can never access it using the paging system inside of a process. So some of these things that happens that gives us the need to have this microkernel is that we need to receive interrupts, we need to handle syscalls, sysinter, stuff like that. Once these things have been received in the kernel mode, we can swap the CR3 to the real kernel process and thus significantly reduce the attack surface to the point of where you can't really get an exploit running. The real kernel still does everything it's supposed to, and in turn, this prevents us from causing access to kernel mode from user mode, meaning that all three attacks are prevented with this. There is a performance impact of this. The guesstimate in the literature is between 0.5% and 35%, a rather large gap. Clementine and Daniel told me they have actually tested this in a paper that will be released, I think, tomorrow, and the real value is below a percentage, if I'm correct. There are some overhead on flushing the paging caches. The question mark is in here because I wasn't allowed to talk about it. It doesn't actually, rarely does it when it happens. The manual says it can, and usually it doesn't because it doesn't need to. It tags with the CR3 value. There's some overhead on swapping the CR3 register as well. So we are safe again for a small price. And I can assume you can all guess what happens now. Well, this guy is kind of getting annoying, isn't he? It turns out there's another attack through the branch target buffer. And this was released last year by Otushkin, Pomanev, and Abu Ghazali. And it works because modern x86 are superscalar, meaning that they're able to execute multiple instructions at once. And also, modern x86 processors are so-called pipeline designs, meaning that different stages of processing instructions running simultaneously. It looks something like this in the pipeline. We start in the up above and decode the instructions, and meanwhile, the execution units, which is the colorful things that are down below, are executing instructions simultaneously, as many as it can without dealing with dependencies. Just executes as much as it can, and then submitting those to be submitted to the architectural state later. So what happens if we have a branch instruction coming in the instruction decoder? A branch instruction would mean that the instruction decoder would have no idea where it should pick the next instruction to decode from. So we have two options here. One option is we can either stall until the branch instruction is executed and then start passing instructions. That will leave the execution units with nothing to execute for a small period of time, a so-called stall, which of course is expensive. And the other option is we can try to predict where does the branch go. If we turn out to predict it wrong, we have a mechanism that we can use to do rollback. So all modern CPUs choose the second option, that is prediction. And Intel, for that, have a branch target buffer. It stores the last target address of a branch in a cache and uses this for prediction. Where does a branch instruction really go? Where does the instruction decoder need to get its next instructions from? There is a very interesting thing about this cache. It uses only 31 bits to index. What does this mean? Well, typically user mode addresses in modern operating systems are all using addresses where the 47th bit is 0, and the kernel mode addresses has the 47th bit set to 1, meaning that conflicts can arise between kernel and user mode addresses. The two addresses that I have here are two addresses that will have a conflict in this cache, because they use the same position in the cache because they're tagged on the identical lower 31 bits. So if there is a conflict in a cache, it means things will not go as it should, meaning that things will be slower. And I guess that Dimitri, and Abu Ghazaleh said, oh, challenge accepted. So how does this work? You initialize the cache by doing a branch to an address A. Then you do a syscall with a branch instruction. You time the same branch you did in the first step. And if it's slower, address A has the same 31 lower bits as one of the branches in the syscall. And then you just repeat this for all possible values of A. And, well, so at some point you'll hopefully get a conflict and a lower timing, and you'll know exactly what this call in the what this branch in the syscall at what address it is, at least the lower 31 bits. The unfortunate thing here is that while we can only de-randomize the lower 31 bits using this method, that is exactly what modern operating system does to randomize the kernel, meaning that we can de-randomize the kernel. And here, with this attack, we're not depending on actually accessing kernel mode. We're just depending on having a branch at a certain position. So the kernel as a process mitigation that I showed before will not fix it. In fact, Felix Wilhelm, in 2016, could use this method to de-randomize kernel mode address space randomization in a hypervisor from unprivileged guest. So that's quite kind of nice. So can we map the kernel? But this method, of course, has some problems. One of them is we cannot map the kernel like in the previous attacks. And there's a question mark at the end of the statement for reasons, because while we can only locate branch instructions, how about branch instructions in the pagefall handler? If we can locate instructions in the pagefall handler that are only called when you access a mapped page, well, then you can figure out which page are mapped again. So I have not actually finished the research on that, so I'll just leave it as a thing to think of. So now we are reaching sort of the conclusion part of this talk. How can we mitigate attacks on KASLR? Well, we can use a combination of kernel as a process and randomizing through the upper 17 bits like Microsoft do for the self-reference map. That leaves the question, should we? And first of all, we should consider that these mitigations are a mitigation of KASLR, which itself is a mitigation. And we should seriously ask ourselves the question, is that where we want to go? Also, we should consider there might be more leakage in the CPU. Especially, it'd be interesting to see attacks like the one I sketched before, where we used, say, a branch in the pagefall handler to find out if pages are mapped or not. It would be interesting to see what we can actually do in that direction. That might not be mitigated by the two mitigations mentioned above. And finally, we should consider that there are software attacks on KASLR as well. And Gel Beniamini from Google Project Zero wrote, while those attacks, meaning Prefetch and TSX, are quite interesting in their own right, it should be noted that bypassing KASLR can often be achieved much more easily. And if we think that these attacks that I've just sketched are very complicated to mount, they're not. So if it's easier to find a software break for it, well then maybe, yeah, KASLR isn't that important in real life. So should we drop KASLR? Everything we've seen so far lets us assume that KASLR is broken. But every break that I've shown so far, even that of Beniamini, has a thing to it. They are using arbitrary, unprivileged execution on the CPU. And that's not always given. There's a class of attacks that use, say, fonts or other data bugs as format, and they still, to some extent, break because of KASLR. KASLR is implemented and mostly bug-free, and with low performance overhead in general. So maybe we should probably keep KASLR against these attacks, but realize that we need to write safe software in the kernel as well, otherwise it'll be vulnerable. The KASLR is not a good fix for it. So a bit of look into the future. Intel will introduce a 5th paging level, giving us a larger, 9-bit larger virtual address space, meaning that we have more entropy for kernel address space randomizations. Here is an opinion. I don't think that more entropy is likely to fix this problem, because we can observe the cache level with Prefetch and TSX. We can do a breadth-width scan doing half terabyte steps at a time, meaning that we're likely to be able to run through even a 57-bit virtual address space in a reasonable time, unless they change other things in the CPU. So thank you. I hope the picture here looks something like the picture that I painted of KASLR. There's a nice romantic hut on a lake and a big ugly duckling swimming in the lake. So thank you.